So let's start our last session as part of the Atattva Jnana. So till now we have at least learned what zero knowledge is, and later learned or listened about what snarks and starks are, listened about Groth 16. Kinda if you also followed the workshop took by Arnav, you typed some Python code regarding starks. And now we are on the ultimate part of this workshop where Ayush, who works at ZisK and expert in zero knowledge and zero knowledge virtual machines, will be explaining about what a zero knowledge virtual machine is. And Ayush, over to you.
Okay. Thanks, man. So to start with, I'm not an expert. I'm an enthusiast. Before I dive into it, how many of you guys have worked with ZK circuits? Okay, no worries. That's better. Okay. How many of you guys know how a virtual machine works like? No worries. We'll cover that up. Okay. So without any further ado, let's start. Before we dive into it, I just want to know that this is my notes. So it's pretty descriptive. So at any point in time you feel like you have a question, you can let me know. If I don't know, I'll say I don't know and I'll get back to you. Okay? Perfect. So I hope you are aware about what ZK is, what zero knowledge is, and the complete purpose for writing a ZK circuit, right? So even to begin, I would say one of the most integral part of a circuit is to cater to both soundness and completeness of it, right? And in order to do that, you'll basically write a circuit, but it's like you'll end up writing a circuit that is under constraint. So what is an under constraint circuit? Let's take an example for this door. So you wrote that you want a door that can have this dimensions, but you want anyone to enter from it. Now that's a very open-ended circuit to write. Now let's define it up that we only want a bottle to pass through it, right? So you've had a door that has ample amount of space for anything to pass through. That's an under constraint circuit. Now, if you throw a chair out of it, it'll pass through. So how you narrow it down is basically a very abbreviation of writing a constraint circuit, right? Writing that, it's pretty difficult because there are edge cases and scenarios that you'll have to think about. And while you are doing that, you'll have to write it in a language that's very close to a PIOPs, right? Do you guys know?
Can you repeat what it is?
Yeah, so it's basically you'll have to write it in an individual language like SIRCOM or individual DSLs that are relatively made for writing circuits. Now the problem with that is they're very constrained up to, or they're not flexible enough for you to give the freedom as to what all you can write it on, right? You'll have to look through the constraints, put it up together. So to sum it up, it's pretty difficult in writing in an individual DSL. That's how we basically began to think about how we can make this part easy. So the idea of building a zkVM was to make developer experience fluent of writing ZK circuits. So while we begin with it, so to give you an abbreviation of what zkVM is it's a virtual machine that utilizes zkPs to guarantee the integrity and privacy of computations. So it's like a program that runs programs and gives an attestation that your program is true, right? So I should have used an extended display. Now I'll have to read it from there. But yeah, so that sounds fancy, but how do you potentially put together a VM, right? So to put together a VM, there are multiple components in it. You'll need to have a compiler, a VM, a prover, and a verifier. All those components that are potentially, so if you see, you eventually did not need to have this part while you were writing a circuit. You need to just like have a simple prover that can prove the circuit is constrained, or like even if it is true. A verifier to verify that the computation that you did throughout was true. Now, in order to build this up together, we'll move into each component and see how are they being built and how things are basically running at this point in time. It's pretty simple, straightforward, a general compiler, how it works like, straightforward on that approach. Any questions? I don't think so. Yeah, perfect. Do you guys know what LLVMs are? Okay. So LLVM, consider it as like you're writing a language. It's very centered towards a particular architecture, right? Now, if I potentially say that I need to write Rust that's compatible to, let's say, ARM or x86, how would you do that? So you will potentially write a single state format of interpretation for that. But let's say if I potentially put together a format for you to have a bunch of languages, for you to be able to like put everything together for a specific architecture. That's a very base idea about like how LLVMs are. So it's basically a set of compiler and programming toolkit that can be used to develop a front end and a back end for language. So consider it more like, so consider it more like, in order to write more fluent circuits, you need a language that you prefer and an architecture that's compatible enough for a VM to work at. So in order to find a middle ground, LLVMs were about. This LLVM as a concept is very old, so you can go read about it. It's a very old concept to start with.
So, is it like the intermediate language to which languages are compiled, and then that language is being compiled to?
Yeah, so it's okay. Good question, but it's like, okay, let's dive into it. So it's not like a language. It's a programming toolkit. So understand it from a toolkit perspective. We are basically extending a language and its integration to a native, let's say, machine types. Okay, so how this particularly like works like is the language you're compiling is put together. Yeah.
Compiled into another representation.
Yes, exactly. So you have an LLVM IR that's then optimized and the state compiler, and that's how you potentially put this together.
Kind of like how Java is compiled.
Yeah, exactly. So you might have seen like, have you guys heard about zkVMs? I should have started with that. Okay, no worries. So it's basically, that's good by the way. So there is a battle that's going on for zkVMs. But yeah, so think from a perspective that if the idea is to improve developer experience, you need languages that are more refined, more flexible in order to write more sound and complete circuits to an architecture that's relevantly compatible enough to give you that freedom and then be able to compile or like generated proof out of. Right? So yeah. So in like a general sense of like how an LLVM function looks like, it's a simple syntax of like how you'll have an addition of two numbers being put together. So it's, I would say it's more on the context of like compiler design, which you'll learn, I hope, further. If not, no worries. What is RISC-V and why is everyone talking about it? Yeah. So, do you guys know about?
I have heard about it.
Oh, that's nice. Would you like to tell?
No. All I have heard about is like it's open.
It's something, yeah, it's something there. Okay. So, the reason it's been out there for quite some time now, and the reason it became very hyped is when Vitalik the founder of Ethereum, said that we'll replace EVMs with RISC-V. So that's a very big statement to put together, because you're basically changing the complete interpretation of a VM to a different type of an IR. So this coined up a lot of things, but there are multiple ISAs. So RISC-V is an ISA. There are multiple instruction sets that are there. By the way, any questions at any point, please feel free to raise your hands or just speak. Right? So think from a perspective that every languages that are compiled will have to be compiled into an interpretation. That interpretation is to be utilized further. So let's think, why did we even start with like domain specific languages? We could have basically started from Rust. We could have started from C to write ZK circuits. Why was that not possible? The reason was pretty straightforward, simple. You needed a language constrained enough to write those individual formats of circuits. You start with a language that's from grounds up designed for this. So that's an easier and more straightforward approach when it comes to implementations of it. That's the reason we were able to like start with these kind of languages, DSLs, and you'll see more DSLs out there. So Noir, Circom, and Halo 2, and bunch of more there. So that was the reason for us to like start this particular format of interpretations and development of things. There are a bunch of ISAs. Now the format is very debatable as to which one should one choose. Should I go with a custom IR, or like should I build or like use an existing ISA? So think like if you write a language that has a certain set of opcodes, and those opcodes are by default designed to follow a ZK constraint, right? Then think from a scenario that you have a language that's a general purpose language, and you utilize that to basically build up a more proficient technology on top of it. The debate is basically optimizations on the proof side and feasibility of it, right? The best scenario is to go for a middle ground. That being said, there are multiple systems out there that have tried to work it through with different types of ISAs. So to give you an example, I think this. So these are, have you guys heard about any of those names towards the left? Okay, perfect. So these are some of the teams that have been building around zkVMs. Right. Now, if you recall, the complete architecture of a VM was basically to be divided into compiler, VM, proving system, verification. Right. Now, this is how a general diagram looks like. StarkNet is using stacks. You guys might have read about what stacks are and how stacks work. Now, think of like writing a stack. I guess you did Stack 101, so you wrote it in Python. Now think if there was a language that could potentially give you that benefit out of the box. You wrote A plus B equals to C, and you could potentially generate a proof out of it, rather than writing the complete interpretations for it. That's what Cairo did for StarkNet. There are multiple languages out there, multiple ISAs that have worked it through. These are some of the teams that have been working around the zkVM space. StarkNet, Lita, RISC-0, Succinct, Nexus, Polygon Myton, and a bunch of more. So if you think from a moduled perspective, you learned how stacks work, right? Consider zkVMs to be incorporating stacks or any other proof systems into it, but you're not actually writing those proof systems, you're utilizing it out of the box. So it is basically giving you a nascent state of technology that could potentially be helpful for you to generate proof out of a complex computations, right? So as an example, if you write a circuit for, let's say, a normal evaluation of, let's say, Fibonacci, that is going to be insanely big, because every step is basically a constraint that you'll be writing it out. Now, generating proofs, and that is going to be another hassle to work with. So zkVMs potentially moduled it up and utilized these things as a default. Now you have a VM that utilizes individual or a combination of proof systems to be utilized, right? Any questions? Yeah. Ayush naam hai mera. So
why should
सीधे
we
बोल
worry
सकते हो.
which compiler they are using?
Yes. So think, let's say you're writing Rust, but you're not using Rust C. You are basically, let's say you wrote another compiler that has an implementation of multiple opcodes opt together. So you basically wrote a compiler that is centered towards, let's say, a chess game written in Rust. So that's what the approach is. So it's consider it more like a program that is proving programs. So you'll write a compiler very centered towards the program that it is compiling, right? So it's like you're optimizing, you can optimize on any ends. So all the zkVMs are potentially optimizing on one of the columns. You'll see them optimizing on like compiler, VM, proof systems. These are the three columns that you'll see any zkVM optimizing on. So if you put a cluster to it, think that they're basically, you can optimize on compilation. That's what gives you, when you're utilizing a custom IR to an IR that's already out there. So you basically wrote an interpretation that's native to the machine that you're building. So anything, think from like, okay, so how many of you guys know what zkSync is? Okay, no worries. So consider you wrote something, a language, compiled into opcodes. Now, those opcodes have a certain, let's say, gas to be evaluated on, right? So what you did is basically you wrote a language with a compilation of, let's say, 15 different variables, 15 different things, but the opcode that you're using is a dependency on the language itself. So you basically wrote a new language compatible or like derived to a new IR, and that is what an IR is. So that's where you'll use an LLVM to put together a front of like pre-utilized languages. So let's say Rust C to a new IR of sort. So yeah.
So somehow the program we are writing is related to compilers.
It's like your program is being compiled, but that depends on the VM you are utilizing. Is it a predefined IR like a RISC-V one, or you basically wrote a compiler in itself? So like if you're writing, let's say, Noir or Circom, so that's a new language to work with. Now you'll need a VM that interprets that languages. Those languages are basically compiled to opcodes. Those opcodes are basically being utilized further. So
You made the program so that like so many languages can be interpreted, the efficiency becomes less.
it's like more on the lines of like how efficient is your system, and you basically have two options. A, you choose an efficient language, or you build an efficient compiler. So think okay, we will come to this, but this might help. Okay, so you might have seen proof generations and things. Okay, so think that your language was compiled and executor gave a certain set of programs. Now this is a very generic format of things being compiled into. Anything that you can do, so this is a prover side, right? all the optimizations in this case would be prior to this. So anything that is like, you basically defined a VM that is generically utilizing a language, compiling it into a different set of instruction sets that are being core to a different proving system. So like your stacks could utilize or like work on those instruction sets. Any more questions? Okay, so while we are talking about instruction sets, the best thing or like the reason why RISC-V is a standard or like close to a standard is basically when you're working with an unconstrained system, you have no idea what is going to come through you. So you need a very specific state format of representation that gives an idea that, okay, so these are the 47 instructions that I'll have to work with, right? So that's what RISC-V, or like there are multiple ones, but we'll see like why RISC-V is chosen. So think, have you guys worked or known like RISC? Okay. Let's take this as an example where like all the constraint defined into this specific set of instruction set are numbered. So you have nearly 47 instructions, a combination of memory or computations, arithmetics, so like adding A plus B or like A add B, jump from A to B, so A jump B. So these kind of instructions clustered into different flags. So it's like having a general purpose register from 0x to 31, and we'll have a bunch of base instructions, memory instructions, arithmetic instructions, and more. Most of the zkVMs currently utilize 32-bit RISC-V. That's like having a memory space with
4 gigabytes.
Yeah, exactly. 4 gigabytes of space for you to work with. Now, you guys have heard about trace generations or like traces being generated out of it. So from a very nascent example, let's think that you had a VM or like an architecture of this particular set, and each computation generated traces. So like if you added A plus B, you'll have to load it into memory, add it, store it, put it out. Yeah. So different modules, different flags would use different aspects of it. Every aspect would generate traces, right? When you're basically working with a computation that's large enough, traces are even more large. So I'll probably run it through, but like any questions in the middle, feel free to ask. So think that, okay, so we had this. The reason it's very specific or like being utilized is
What are we exactly trying to achieve via RISC-V?
yeah. So we are exactly trying to achieve that we know what are the instructions that are coming. So let's take an example. If we had to basically implement a simple logic with x86 and RISC-V, it would potentially be a multiple of 10x with x86 versus RISC-V. So with RISC-V, we have a limited known set of instruction sets that are predefined in order for you to work with. So your language has a known set of constraints or places to which it needs to satisfy to. So that is the reason. So again, we're optimizing on VM part. a simple definition of basics that we have learned now is to understand how everything comes together and what actually is like bringing together this format of a RISC-V VM of sort, right? So the complete idea is for you to be able to write your Rust code and get a program result, right? The point is how you do it. So that is where the complete scenario is going to be defined towards. You'll have a format of interpretations being done. A general format is like your Rust code compiles to an LLVM component that could be x86, RISC-V, or that part. So whatever we have learned up till now is this part. This. कुछ क्वेश्चन है भाई? ऐसा साइलेंट बैठे हो, कुछ समझ में नहीं आ रहा क्या? क्या हो गया? हाँ मतलब सो दिस इज लाइक बहुत ही फंडामेंटल से स्टार्ट कर रहा हूँ. सो थिंक इट मोर ऑन द लाइन्स दैट यू लर्न ZK, बट थिंक दैट इफ यू हैड टू राइट a program to prove if I sent $100 to you.
But it's not about the language, it's about the machine.
Yes. So it's like utilizing the same core functionalities of ZK, but in a more optimized, more refined manner of things. So this is more like the history or like journey of how zkVMs are being built. An architectural side, it's like, okay, it's like learning C for programming.
So currently, what is it? ZisK is optimized for only Rust.
No, so it's like there are multiple interpretations that it could compile to. So RISC-V is an output, if you see.
Okay, we convert. Okay. But it got it.
So see, you basically get this.
Got it.
So to put it very simply on the ends, I would say it's like why most VMs are using RISC-V, I say, is A, it's simple decoding. You know what are the constraint gates, specific number of gates, so you know what you're compiling into, and it gives you a much more straightforward approach to interpret things. B, explicit semantics, so no unambiguous circuit definitions. There are no predefined obligations that you need to work at. Small base set, minimal constraint overhead because it's limited toward a particular size. B, it's open-ended, it's open source, anyone can use it, open for people to use it. Now, let's see how does our zkVM works. Okay, so we basically were able to understand, or I was trying to make you understand, how this part of interpretations work like. Because as you dwell down into more things, you'll potentially be working more closely to programs being evaluated, right? So a general state, or like, so this is more like a templatized version. If you had to, let's say, work with a zkVM, this is how you'll work it. It's defined into different stages. So it's like the compiler stage where you compile your program into a machine defined ISA. This could be anything that you could define. Then the VM stage is basically when you utilize those machine codes, generate an execution trace. And the traces could be a format of like arithmetization. So you might have worked with a few arithmetic, right? So yes, this is where it gets interesting. If you potentially had to write everything down from scratch, getting to this would be very difficult. For it would be very specific use case formatted. But if you had to make it more versatile, you need something that could be interpreted into a generalized format of things. So you're basically generating traces, evaluation of traces. These traces are compiled into arithmetizations. Those arithmetized. So this is important. Okay. So by the way, this is more focused towards snarks. So like this particular example. So you had your traces converted into polynomials, commit to those polynomials, and evaluations of those polynomials would be very centered towards definitions of it. So in this case, you could commit, challenge, evaluate, and have a Fiat Shamir implementation and generate an evaluation or a proof. So this is where the core of the next segment would be, the proving side of things. This is what makes, I would say, different zkVMs have a different approach towards generation of it. Then once you have generated the proof, it's basically verifying it. कोई question? ज़्यादा boring हो रहा है क्या? या एकदम ही ऊपर से जा रहा है, मैं समझा नहीं पा रहा हूँ कुछ. Okay. Now, this is how I would say things usually get into things. You write a program, parse the inputs, and generate a receipt. It's eventually writing similar as circuits, but you're not actually writing it into a specific language. You have a defined proof system that works on those definitions and generates the proof. This is an example of a zkVM called as RISC-0. So RISC-0 is basically a zkVM defined. I will speed run over it, but think from a perspective that you wrote a program, passed the inputs, and you generated a receipt. What is a receipt? A receipt in this case is basically a proof and the output. So it's like having a proof with an output that satisfies those proofs. That you did a particular computation based on this particular numbers and you had a proof generated out. Let's speed run RISC-0. I would potentially start something here. So this is how a general state VMs would work like. In order to have multiple languages being compiled, for now RISC only works with Rust, but there could be integrations that could potentially lead on to having more languages being compiled to it. So you're compiling into a IR, those IR being compiled to a RISC-V binary. Yeah. Question? Then it's potentially a VM. Now that VM, as we looked on earlier, the primary task is to have those traces, constraints, results, plus a lot of math put together to generate a receipt. Do you guys know about fold recursion?
Like, as in weird.
Yes, yeah, it's a type, but like folding schemes or like recursion. Okay, tell me differences on the part of snarks and starks. Do you guys know about like proof sizes? Which is bigger, which is smaller? Yes. Yeah. So think that you wrote a virtual machine that is generating Stark proofs. So ultimately, you'll potentially have to work with a proof that's way bigger to work with. Now, bigger proof will take a lot of time to be verified. Okay. One of the things what RISC-0 does is basically recursion circuits. So what are those recursion circuits? Think that you had the receipt. Receipt is basically proof plus output, right? Now, in order to have a much more efficient proof, you utilize a combination of snarks plus stacks, where you utilize all the stack proofs, pass it through a recursion circuit, and have a snark proof generated. Now, what are those recursion circuits? Let's say you generated a trace of an arithmetic component, right? Those components were utilized, you generated a proof. Those proofs are potentially merged together and you have a final proof. But if there was a bug in, let's say, any of these one, how would you detect that? So a recursion circuit is basically a circuit that verifies proofs and merges it with the other one. So every time you are having a recursion circuit, it's basically verification and adding of two proofs. So that's how you potentially, so the architecture for RISC is merged together on the format of snarks plus stacks, where you utilize stacks to have a faster speed and snarks to have a more composable proof for you to verify. Right? Have you guys worked with a zkVM? Would you like to? Okay, perfect. Let me. Okay. So before we start, let's say, would you guys like to do? I can share this code also. But yes. Okay, it's a very dumbed down version of it. But once you're working with RISC, think there are three main programs that you need to work with. Three files that you need to modify for proof generation: host, guest, and methods. So these are the three primary files that have to be modified. Would you guys like to do a code along session, or? Okay, in that case, let's do one thing. Let's try this. So this is the zkVM that we are working with. So I tried to write down a simple Fibonacci program that would be generating a proof. So a normal, this is a simple Fibonacci example, constrained up to putting together or like evaluating 100th position for a Fibonacci series, right? In the host file, all you did was write this, and that's it. It's pretty straightforward, simple on how it works. Like, it's a straightforward thing. all this is, by the way, so when you work with risk, you won't generally be seeing this. This is more for showcasing how things are. But okay, so this is the variable that we are talking about, right? So once you generate a normal proof, so it is potentially doing everything that we talked about. We're working through the program interpretations, utilizing the proving system, and trying to evaluate that program given on the constraint. Now, since you're working with Rust, it gives you a bit more easier format to control the constraints into it. You can potentially write on the parts, if the number is bigger than 50, we don't calculate. If the number is smaller than 10, we don't calculate. Or any format of evaluations that you want to narrow it down towards. Right. Think about proving Ethereum, but into a virtual machine. If you could potentially put together a program that could verify that these transactions on Ethereum happened, and you have a proof for it. So something of a similar side of things are being explored. Okay, so ideally you won't see this as an output when you're working with risk. What eventually happens is the risk virtual machine keeps receipt as an object, and that object is containing your proof and output for you to work at. But yeah, if you want to do it as a code along session, we can start. But yeah. Or if you want, we can move on to a different topic as well. You guys say.
Different topic.
So I'm currently working with a new kind of a zkVM, ZisK, and that was supposed to be the next part of this session. We'll understand that, how that works like, and maybe try to work with that. So which part? Should we stay here? Should we move on to the next part?
Move on to
No worries. So it's eventually, I'll share this notes. You can potentially follow this and have a very straightforward approach with working with risk, or I would say in this case specifically for ZisK, you'll only need to modify, if you're working with risk, a main file, host file is basically update your IO, and that's how a normal proof or like a simple to-do list to work with zkVMs for you would be like. Okay, this is what I am working with. Okay. Now, we potentially talked about RISC-V based VMs, how a general VM works like, and in order to have, let's say, a proof generation, how would a general state of VMs would be like. Now, the complete idea was to have a more fluent developer experience with a much more faster proof generation mechanism to be achieved. So what is ZisK? So ZisK is a high performance ZK machine that is designed to compile and execute general purpose programs to a 64-bit RISC-V architecture and a 128-bit security. So it's potentially like having a Hummer when you can potentially have a Thar. Now that gives a bit of context, right? But we were talking about a 32-bit RISC-V because we wanted a much more faster approach. Lesser trace, we had a very specified area that we know we need to work at. But if you potentially think, it's basically double the size of the previous architecture that we're talking about. So that means it has much more room for evaluation, much more room for you to potentially put together things in a single state of parse that can be done. So we're talking about having like a speed focused spectrum, less traces. Less traces means we'll have a much faster, it impactfully faster zkVM. And in order to do that, less traces make sense. But why do we need a 64-bit RISC-V? Things were running good with 32-bit. The reason and the approach for us to go for RISC 64-bit was that what if the computations are big enough? If you potentially want to verify, let's say, a computation of an AI model into a zkVM, that this particular model generated a particular result and you have a proof out of it. So in order to do that, it would potentially take a lot of space, a lot of room for you to evaluate on.
Is that possible?
Yeah, it's possible. Yeah, so like you can potentially, okay, I should not say this, it's a very political joke, but think of it as like the machine that was said, Alu dalo, proof niklega. This is how you can consider a zkVM is. You write a program, you generate a proof out of it. If you can potentially, let's say, write an emulation of EVM, you can prove the validity of that EVM machine through that. So there are things that are being done. It is a possibility, it's being done, explored, people are doing it. That's the reason we are currently working very closely with Ethereum Foundation to have the implementation of Beam chain with different VMs. So you might also see, by the way, you can follow like a bunch of so yeah, interesting. This is not my site. Yes, so the complete idea is to have Ethereum being proven into real time. Yeah.
Oh, why are they trying to do this?
Yeah, so the reason for this to be implemented is because if you think that, okay, if you basically generated a transaction and you're waiting for the block to be committed, added, right? That takes the end-to-end objective for us to do this is to work around and have a proof generated for those transactions under 12 seconds. So that's an estimated time what it takes for the blocks to be added. Think. Now, the reason we need this is basically currently in order to do that block building, you need a very high compute machine, right? Let's say if we come to a possibility where we need or where you could potentially generate your proof of your transaction on your phone, right? In order to have a much more efficient format of things being done, that's something that is being explored. If you look around client-side proving, yeah, that is being done, being proven, being explored. But yeah, let's get back to what we were discussing. Okay. Didn't I said that we need a lesser trace machine to have a much more faster and efficient VM? That's not technically true. Less traces do not mean a smaller architecture. It's potentially saying you have the size of the room that's already there and you need to prove like the volume of the air inside this room. So you eventually start to think if the computation size are very high or very large, you eventually need a machine that can work with these high set of computation requirements. That's the foundation for us to explore or like work with this. How ZisK is being built. So think of it as state machines. So it's relatively a similar architecture. Okay, so you're potentially working with different components all together. ROM, processor, RAM, arithmetic, binary components, and other coprocessors that you could potentially define. Right. And let's take a scenario where you are potentially trying to evaluate a computation, and that is going through multiple rounds of evaluation. So, okay. Let's take a mark.
Actually, can use a blackboard.
Okay. Let's say we want to potentially prove A plus B equals to C. In this particular format, the instructions would be loaded onto the machine. You'll have to add them, store them, evaluate them, right? So on a very idealistic format, so this is going to be a very dumbed down version of it. But ideally, what you'll do is have different components being utilized for the sense of things that they're doing. So think you need functions to be loaded. That's the first thing that you'll potentially do. So the memory component, then you have arithmetic component or the ROM. So ideally, you'll have this particular equation divided into the relevant task each machine would be doing, right? This part is going to be with, let's say, memory machine to A, load A, PC1 to then you'll have maybe a bunch of jumping statements or any state of computations that you do. It's like a normal state machine, right? Nothing special out there. But it gets tricky when the program gets bigger. You'll have more computations to be done in the format where different individual state machines are working on different architectural sets, right? So that's how we are kind of working on the architecture of ZisK. So it's fundamentally designed to be like an embedded machine, where you can divide the tasks that you're doing into different processors, and those individual processors are required or working on a single set of constraints that they're defined into. Now, how do you prove that, let's say, you had a statement that said load A into the memory, or if this particular computation that was there would have a dependency on multiple state machines, right? And in order to have a sound proof, you need to prove that all the state machines were doing exactly what they were told to do, and the computation passed through every constraint that was designed, right? So there is a language, or I would say we potentially need to evaluate the computation for each state machine and have a net sum to be 0. So think of a polynomial constraint where you define every state machine or dwell it down to a polynomial, and an ideal scenario for a sound proof would be the sum of all polynomials is 0. Right. Now let's take a step back. How you define that polynomial? How do you build that up? Writing a polynomial is going to be difficult. So there's a language that you're working with. It's called PIL. So you guys can read about it later, but yeah, think of it as a very dumbed down version where you could write polynomial constraints into a language. Right. And that language is compiled into an interpretation that is somewhat, I would say, you guys might have heard about air constraints. R1C is relatively similar to an arithmetized constraint. Right. So in order to have a proof generation, see, so we were potentially doing this for the prover stage. We were generating traces. Those traces were eventually arithmetized, and those arithmetized stages could be R1CS or Plonkish or air. You guys have worked with snarks, right? R1C is something that you guys might know about. So consider it similar to an interpretation whereas it's air, right? Ultimately, do you guys know about what lookup tables are? It's okay. It's similar to like having a table that contains format of witnesses, inputs all together combined. So in order to have a more synchronized reference point, you need to check that, okay, if memory needs to work on a certain set of constraint or variables, where should we reference back to every time we need something? That is a very rough way to put together a lookup table. So it's like having a table with certain columns that has a reference points for variables, or I would say constraints being added to that table to have a reference what are the constraints that we're working with. Yeah. So it's a bit more detailed, but to think, I think I added an example to this. Wait. Okay. So think you need to potentially work with a computation. You need a reference point for each state machines to get back to, right? That is a very dumbed down version of potentially putting together a table that has constraints, witnesses, and set of variable that you can reference back to. Okay, so if this is a constraint where you can potentially prove that A, B, and C that you're working with exists or are the same that you're working with, is something that you reference back from the table. So in order to have a more synchronized way of referencing the things that you're working with. Why did I bring this up is basically, let's say there are different state machines working with different set of instructions, different objectives. Now you need to have a single state reference point to get back and have a provable point to prove that this constraint exists, this variable's positions exist, these columns exist with a certain variable, right? So the complete architecture is focused towards having different state machines, referencing back to a bus that is native for computation. So think that you potentially had a state machine defined into pill. Those polynomial resulted into arithmetized representation here. Now, in order to prove that the complete execution was right, you need to put together a foundation that evaluates the sum of all the state machines and get to a resultant. Right. That's the base of evaluations that you're working with. Oh, yeah. How do you work with ZisK? You take your program, it's compiled to RISC 64-bit interpretation, put it to a VM, and we generate a hash of the program that we're actually executing the same program that we're saying that we're executing. B, you generate the proof out of it, and you put together the proof, the output, and the hash of the program to actually verify if the same program was executed or not.
So we are revealing the hash to verify.
Yeah. So the reason we need to have a hash of the program is in order to have a metric to prove that this is the program that we're actually evaluating.
Like it's just to
Yeah, it's just to confirm.
It's doing whatever it was.
Yeah,
supposed to.
exactly. Yeah, sure. Okay. I can actually do it.
That does not reveal the inputs.
Yeah. So, okay. Think the inputs are basically parsed onto the prover. What you're potentially trying to do is have a hash of the ELF that was generated. So, like the interpretation that you did, you have a hash of the same program that the proof.
ELF is RISC-V output.
Yeah, exactly. Think of the same thing. Now you'll have the same ELF hash that is proving that you executed the same program that you are saying that you executed. So the proof is basically, so once you verify, the verifier takes the proof, the public output, and the program's hash that you are verifying. So eventually you end up verifying that this is the program that I worked with, this is the proof, and this is the output that I potentially worked with.
Why program hash?
Yeah. So it's not a necessary requirement that you'll see most of the verifiers using. So in order to have a more complete, I would say, approach towards verifying that, okay, so this is actually the program that you actually executed or not. So it's like, okay, you can write a verification circuit that verifies that given these constraints or these constraints were followed or not. Now it's potentially saying these constraints were followed for this specific program given the proof is this and output is this.
So program is also hidden.
So it's like
The input is
you're not hiding the program. So you're basically running the program inside the prover. You're generating the proof with the outputs, and in order to verify that, you're the verifier is also taking the hash of the interpretation that you worked with.
Then why do we think
Like, why, like, if the verifier is taking hash of the program, then the prover should also provide the hash, right, to check that both the programs are true. The proof includes the hash of the program.
So the proof includes the computation,
Includes the computation, but
proof of the computation.
why isn't the prover providing the hash to the verifier? Prover should also provide
the proof includes the hash of the program?
Huh. So like, okay, so correct me if I'm wrong. So you guys are saying we need a hash that also has to be the part of the proof to the verifier so that we can eventually put it all together.
So that we can evaluate that we can match that my program dot hash. We should match the verifier should match the hashes, right?
Yeah, so you know,
prover should also send the hash.
Yeah.
Because what if it's a malicious program?
yeah. So that's how you basically work on the underlying. Okay. So think, yes.
My program dot hash to
Yeah. Okay. That.
Yeah.
That's
So think. Yeah. This is how you use it. So you eventually compute the net evaluations together. That proves that the complete evaluation was true, plus the proof that was generated alongside is a proof that these constraints were followed given this size of the program, working on these particular arithmetics, and you are able to achieve a format where you can mathematically prove that the certain set of the constraints were followed given the execution metrics and have so think why the reason why we're not directly putting it or generating a proof out of it is the part where, let's say, we're mathematically working on each set of constraints that are there on each state machines. You parse the program, you eventually generate the net evaluations of the program being true. Now, in order to have the complete proof being verified, you need the program that was run, proof of it, and the output of it. So it's basically a false if mechanism. It's not like it's necessarily verifying the program it does. It's an addition to what the complete verification is. So you're basically verifying the proof is alongside the output is of the same hash of the program.
So basically,
how is the verifier doing that?
So how is the verifier doing this?
Verifying the whole thing.
Yeah. So we are potentially putting together the format where you eventually verify or like have an interpretation where you basically, let's say, okay,